My pleasure to introduce our semi-local speaker, Anton. As I heard you were chatting, Anton is simultaneously in Greeley, Colorado, and in China, like Schrodinger's cat. But we're catching him in the state which is in Colorado right now, and he's going to tell us about discrete Painlevé equations, which has been so. A little bit of background. Anton is sort of an integral system, algebraic PDEs kind of person, but he's found more and more applications of this of a connection between PDEs and the algebraic geometric surfaces, which is why we like to listen to him.
Thank you. It's nice to be back here, and I gave a talk about similar things a few years back, but I think most of the people here will be hearing for the first time, and also it will be much more informal. And so I apologize, the talk is student-oriented. I'm also explicitly not following Ranson's instructions, which were give a 15-minute easy introduction, let people escape, and then do hard mathematics. So instead, I will give a 15 minutes difficult introduction, and then explain easy things on the board. Okay? So, and in this first 15 minutes, I really want to explain the name, because for people who are not working in applied mathematics, mathematical physics, when they hear the word Painlevé equations, it's like, whatever. So I want to tell you what they are, and why they're important, and why discrete Painlevé equations are important. So, Painlevé equations are, as usual, named after someone. In this case, someone is Paul Painlevé, who was a French mathematician, politician, and a lot of different things. And the motivation is actually very interesting. These equations are over 100 years old. And at the time, the theory of classical special functions was rapidly developing. Okay? And where do special functions come from? Like, where does Bessel function come from? And it comes from a differential equation, right? You try to solve some applied problem, say you're looking at vibrations of membrane, you're looking at it in a circular domain, you rewrite your Laplace equation in polar coordinates, there is some differential equation that pops out, and that differential equation cannot be solved in terms of elementary functions, so you solve it in terms of power series using the method of Frobenius, get some power series decompositions, show convergence, say this is a new function. So in fact, exponential functions, sine, cosine functions appear in exactly the same way. They're defined by differential equations, and their properties are defined by differential equations, and they have really nothing to do with all these triangles that people draw in school. So, and then the question is, okay, great. We have interesting equations that define interesting special functions. But there is this sharp division between linear and nonlinear mathematics. So linear mathematics, like linear algebra, linear differential equations, we have lots of tools because we have superposition principle, we have the vector space structure and the space of solutions. So on nonlinear, until the birth of the theory of modern integrable systems, about, I think, 50 years ago, 60 years ago now, there were just sort of isolated examples of nonlinear equations where exact solutions can be found. So Painlevé was interested, can we try to define special functions as solutions of nonlinear differential equations? And then there are problems. And one of the main problems is when you work with like algebraic functions, you're really working on the Riemann surface of the corresponding function. You need to construct this Riemann surface. And to construct this surface, you have to take into account various singularities. And in linear case, you have complete control over singularities of your solutions because they're determined by the equation. In the nonlinear case, singularities of your solution are determined not just by the equation, but by the initial value problem. Depending on the initial value, you can have different locations where your solution starts getting singular. Now, if these locations are branch points, then you're in trouble because really, you cannot talk about the Riemann surface of a general solution. You have this motion on the moduli depending on the initial value. So Painlevé posed the following question. It's like, okay, so can we try to isolate the class of differential equations where this doesn't happen? Okay, so we can have singularities, but these singularities will either be fixed or will be singularities such as poles, which do not affect the construction of the Riemann surface, the corresponding solution. So this is now called the Painlevé property, and this Painlevé property applies for equations of any order, but particularly Painlevé worked with the equations of second order. First order is easier, and there are two remarkable equations that appear in the first order outside of linear class. One is Riccati equation, which can be linearized, and the other one is the equation for the Weierstrass P function. So you sort of see elliptic function theory appearing from that definition. But Painlevé was working on equations of the second order and assumed some reasonable algebraic ansatz. So you solve it for the second derivative, have rational functions as coefficients, and found over 50 canonical forms of such equations. And many of them can be reduced to linear equations or equations that can be solved in terms of special functions, classical special functions. And 6 of them were new, actually 5. And then Gambier found the 6th one. So these are equations for which you can talk about a general solution. And such a general solution is known as a Painlevé transcendent. Okay? That one is hard to get your hands on because you cannot do the power series. You cannot do the method of Frobenius. So there are various indirect techniques on how one can get to it. Okay? For example, this equation P6 was discovered almost simultaneously in the theory of isomonodromic deformations of Fuchsian systems. And this isomonodromic approach is one of the powerful approaches how one can study such things. And if you do mathematical physics, and for example, I can include quantum cohomology into mathematical physics, you will see the word Painlevé equation appearing all over. Okay, so it's quite an important object because they really are nonlinear special functions and they can capture very delicate nonlinear effects. So these are the 6 Painlevé equations that Painlevé and Gambier found, written in some canonical form. Okay? Well, the first 2 are easy to look at. This one, the first time I saw it, it's like, why would anyone write something like this? How is that special? How is this good? How can this possibly be good? And the way to see why this is good is exactly you want to go through isomonodromic deformations, and this equation pops out. Then you also notice that there are parameters. So every equation is not like a fixed equation, but a whole family of equations with these parameters. And finally, by playing with parameters, you can actually do some degeneration cascade. So you can start with Painlevé 6 and send it to Painlevé 5, 4, 3, 2, 1. So you can have that. And then another thing is that for some values of parameters, you can actually find algebraic solutions. A simple example, say alpha is equal to 0. Then y equals to 0 is a solution. That may seem like, right, what did we achieve? Got one trivial solution. But there is a group of symmetries acting on all this that is non-autonomous. It changes the value of parameters. But it also changes, like a trivial solution, y equals 0, it will change it into non-trivial solution, and in this way you'll have families of solutions for different values of parameters. So, yeah, so this is classification.
What was Gauss-Kummer-Hermite?
So for special values of parameters, you can have a solution like that is expressed in terms of Airy function or expressed in terms of Bessel function. So like for Painlevé 4, for example, you choose, I don't remember exactly what you need to choose, But if you choose the parameters in a special way, you will get the solution in terms of Hermite functions. Like Painlevé 2, when alpha is equal to 0, I gave you the trivial example. And now, if you rewrite that as a system and choose, I think, alpha equal to 1/2, that system reduces to Riccati equation. And sorry, not to Riccati equation, to Airy equation. And you can get one of the variables in the system in terms of Airy function and send it to the other. Okay. So that's really where the name comes from. So these are classical differential Painlevé equations that I will not talk about. Then there is a strange name of discrete Painlevé equation. Okay? So what that is actually is changing. The reason for the name was that these are recurrences. Like if you look at this recurrence, it's a second order nonlinear recurrence. Also non-autonomous because you have coefficients sort of floating within. Okay? And that recurrence goes all the way almost 100 years back. But at that point, no one had any connection with Painlevé with this. And the connection was obtained much, much later, because if you take a fancy continuous limit of this equation, you get Painlevé 1. So then you're like, oh, that's a discretization of Painlevé. Let's call it discrete Painlevé. So that's where the terminology was born. And then there was a disaster, because people started getting interested in, oh, how can we create discrete analogs and discretizations of Painlevé equations? And there was a very powerful technique invented by Basil Grammaticus and Alfred Romani, essentially, which is, let's take a nice integrable mapping, discrete mapping, and try to duautonomize it. And I will actually explain this part in the second half of my talk. Try to duautonomize it and impose certain condition that singularities of the mapping do not sort of propagate indefinitely. And then they started getting a lot of equations that have these limits to Painlevé equations. And say, oh, let's call this discrete Painlevé 1 because it has a limit to discrete Painlevé 1. But then they found completely different recurrence where no relations, but also has a limit to Painlevé 1. They say, oh, this is alternative to Painlevé 1. And then there are recurrences that sort of look similar, but you take one limit, you get one Painlevé, you get the other limit, you get the other Painlevé, and that was a mess. And I think, as much as I like them, it's still a mess. You open the papers and there's like streams of formulas. And I'm very bad at equations. I look at the equation and I see nothing. Well, I mean, I see horror, but I don't feel it, okay? Alfred, he looks at the equation, he sees it. I don't know how people do it. So, but there were lots and lots of examples, like in disorganized file. And here we get this preliminary definition that the discrete Painlevé equation is a second order non-autonomous nonlinear recurrence that goes to one of the differential Painlevé equations in some continuous limit. So that was the original definition. Turns out that that's not quite good, because of the ambiguity of continuous limits, and also because some discrete Painlevé equations do not satisfy this definition. Okay? So the real insight came from the Japanese school. It originated with work of Akamoto, who studied geometry of differential Painlevé equations and symmetries of differential Painlevé equations for geometry. And one of his students, Hidetaka Sakai, in his PhD dissertation, gave a complete explanation of what discrete Painlevé equations really are, in the following sense. He created a very nice paradigm that incorporated all of the other discrete Painlevé equations and gave complete classification in terms of algebraic geometry. And the interesting thing is, these Sakai equations, they really appear in a lot of applications, because sort of in this century, people are very interested in discrete analogs of continuous processes for various reasons. And in particular, there's a whole new area of integrable probability where a lot of this is happening. Random matrix theory. And these discrete Painlevé equations appear all over because this is like the integrable case. If you want to have something manageable, it kind of has to be that. Okay? So here's the classification scheme. Okay? So as you can see, it is much more interesting than the 6 Painlevé equations. There are 22. And the letters here stand for some affine Dynkin diagrams that are ubiquitous in mathematics. And somehow you have 2 dual schemes. And the reason for 2 dual schemes is one of them is telling you about the configuration space of your equation, or the surfaces on which your equation lives. And the other scheme is telling you about the symmetries of the equation. Okay? And you can see that I sprinkled here various names for discrete Painlevé equations, and the continuous cascade is right here. So these are 6, or actually 8, from the geometric point of view, classical Painlevé equations. And for example, you have Painlevé 6 here, and its background transformations actually result in this difference analog of Painlevé 5, that you can take the limit, and then this difference equation goes to differential Painlevé 5, whose symmetries are difference Painlevé 4, and the top line here corresponds to what is called multiplicative equations. And this is QP6 that has a limit to P6. So quite fascinating thing. Okay? So the goal of my talk would be to actually explain what is this and why the things here actually connect to the classification of singular fibers on elliptic surfaces. And here's a definition of a discrete Painlevé equation. So a discrete Painlevé equation is a triple where first 2 are some complementary or orthogonal affine Dynkin diagrams sitting in the famous E8 affine lattice, and associated with this second diagram, there is an affine Weyl group generated by reflections in the roots together with some automorphisms. Because this group is affine, it has infinite order, and it also has sort of a lattice of translations. Any translation in this lattice is actually an example of discrete Painlevé equation. So there are 22 configuration spaces. On each configuration space, there are infinitely many different dynamics, but we can look at the short steps, short translations. And somehow, this is completely independent of differential equations. It's an absolutely beautiful algebra geometric construction. So that recovers differential Painlevé equations. So if it weren't for Painlevé, we would have to wait a little. Okay? So my plan for the second part of the talk is to maybe make this very transparent. That's the plan.
Great.